Forming a peptide bond, and remember a peptide bond is just an amide bond between two amino acids, requires the coupling of a carboxylic acid group and an amino group. And when you couple those two together, you form the amide bond that is of course shown here. And what's not shown is that you also would lose water in the process. And there are many reagents available out there to do a peptide coupling. And one common reagent is dicyclohexyl carbodiimide, so kind of a long name. DCC is the acronym we like to use. And like I said, there's many other reagents out there. There's one that's really popular called HATU. There's another one called BOP. There's BOP chloride. I don't know. There's a whole bunch of them out there, but DCC is a very popular agent to do this coupling. So we would put here DCC would be a good reagent to make this peptide bond between two amino acids. Now the DCC coupling mechanism is shown here. So you have the carbo, so you have the dicyclohexyl carbodiimide here, and then it reacts with the carboxylic acid to make a carboxylate, which then acts as a nucleophile here. We do a nucleophilic attack, then we do another nucleophilic attack here, and then we do a proton transfer, or a couple of proton transfers rather, and then we lose a leaving group. And so anyhow, you see we lose this leaving group here, and then we form the peptide bond. Now, I'm not going to quiz you on this mechanism, but if you took upper level organic chemistry classes, this is a very common mechanism, but again, not a mechanism that I'm going to quiz you on. You just need to know the reagent can be used to join the carboxyl group to an amino group to make a peptide bond. Now let's say you had two different amino acids. You have these two amino acids shown down here. You have one with an R1 group, one with an R2 group. If you mix those two together in a flask, and then you try to do a DCC coupling, well, then you would end up with 4 different dipeptides, which isn't very useful, is it, right? And so in order to make the desired dipeptide, what we would have to do is we would have to protect one of the amino groups. Let's say we could protect this one here. We could cover that up. And if we could protect this carboxyl group like this, okay, well, in that case, then if you reacted these two amides, the only thing that would happen is you would react between the carboxyl and the amine, and you would only end up with this one product here. And so we're going to have to take a look at some protection, deep protection here in order to mitigate the number of dipeptides that we would make, because ultimately we only want to make one. And so as I just stated in the previous slide, the N-terminus of one amino acid has to be protected, and in the other amino acid, this C-terminus has to be protected. Then we can end up joining here to make our peptide bond. So again, once the two groups are protected, then we could do our coupling with our dicyclohexyl carbodiimide, our DCC, and then we can just remove the protecting groups after we formed our amide bond, and there is our dipeptide, and we would only get one product in this case. So first of all, how would we protect an amino group? Well, the way that we would do it is by using this compound that's shown here. Okay, the name isn't written on the screen, but this is diterbutyl dicarbonate. The name is in the textbook, of course, and I like to use the shorthand form, which is BOC, okay, 2O, and sometimes people call it BOC anhydride. Okay, so BOC anhydride, but the correct name is diterbutyl dicarbonate. And so you can see that the amine acts as a nucleophile here. And then after the rest of the mechanism, we end up with a carbamate, okay? So we end up with a carbamate. There's my highlighter. So keep in mind that a carbamate is when we have a carbonyl that's flanked by a nitrogen and an oxygen like this. So a carbamate. Sometimes people pronounce it carbamate, but I always call it a carbamate. So we have our carbamate, and if we use our BOC anhydride, or more correctly, our diterbutyl dicarbonate, we call that a BOC protecting group. So we say we have a BOC protecting group on our nitrogen. So oftentimes what you'll see me write, or what you'll see in the textbook, is if we have something like this, I'm just going to draw part of the molecule. They'll put NH, and then they'll just write BOC, and the BOC represents everything that's in this orange square here, our BOC group. And so again, the mechanism of the Bach, the installation of the Bach protecting group is shown here. I'm even going to write on this slide. I'll just put this here as an FYI. I will not be quizzing you on this mechanism. Now that we know how to protect the amine with the Bach group, we have to know how to remove it. And the way that we remove it is by using trifluoroacetic acid. And oftentimes we just use the acronym TFA for trifluoroacetic acid. And this is one of the easiest reactions you can maybe do in all of organic chemistry that I can think of anyway. It works extremely well. If you bring somebody in the lab, they've never done anything to do with organic chemistry before, you could just tell them to take this Bach protected amino acid and treat it with TFA, and it's going to work. And the reason why Bach deprotection works so well is because you end up producing two gases along the way. So again, I'm not going to quiz you on this mechanism of deprotection of the Bach group, but you notice that you form isobutylene, which is a gas, so that's going to go up into the atmosphere, and you can see over here on the left-hand side, CO2, so that's going to go up into the atmosphere, and so you have two gases being formed. So this is a huge driving force towards the removal of the Bach group. So again, to add the Bach group, you use the diterbutyl dicarbonate, and then to remove it, you use TFA. Now, something you've realized at this point in organic chemistry is that all chemists need to know more than one way of doing the same type of reaction. And this isn't really the same thing, but it is another way to protect an amino group. And it's using what we call an FMOC. It's kind of a long one here. The FMOC protecting group. And the FMOC comes from the reagent here, which is 9-fluorenyl methylchloroformate. And so all we have to do is take our N-terminus and treat it with this reagent, 9-fluorenyl methylchloroformate, and we add our FMOC group. And it says here the mechanism for the FMOC installation is very similar to that for the Bach protecting group, but again, I'm not going to quiz you on the mechanism. I just want you to know the reagent. And to deprotect the FMOC, we can't use TFA. We have to use piperidine, okay? And if you don't know what piperidine is, well, the structure is on here. But piperidine is you just take cyclohexane and you replace one of the carbons with a hydrogen, okay? So that is piperidine, and you see the structure is shown right here. And this is another reaction that works extremely well. Why? Because you release a gas, carbon dioxide, and so that drives the deprotection to completion, right? Because the carbon dioxide is going up into the atmosphere and is not coming back. Okay, so now we've seen two ways to protect the amine, one with the Bach group, the other one with the FMOC. What about protecting the carboxyl group of an amino acid? Well, the way that we usually do that is by making an ester. And if you're like, hey, esterification, I know how to do that, a catalytic amount of acid and an alcohol, and there you have it, my ester. You're right. That's how you do it, using the chemistry that we learned before when we talked about esterification. And in terms of the R group, okay, what are the R groups? Well, it turns out that methyl esters are really popular and benzyl esters are very popular. And you can just hydrolyze the ester in order to remove it. You just treat it with a strong acid or strong base. Now, if you're thinking, why benzyl? Why are benzyl esters so popular? And you can see the structure of a benzyl ester is shown here. So a benzyl group, a benzyl, if you haven't picked up on it by now, is just CH2PH, okay, aromatic. Okay, so this would be a benzyl group here. Okay, so this portion here is the benzyl. So we have a benzyl ester. Well, the reason why benzyl esters are so popular is because, sure, you can remove them using HBr and acetic acid, so just acidic conditions. However, you can also remove them using hydrogenation. Okay, so no strong acid, no strong base. Just treat them with H2 and platinum, and you end up removing the benzyl ester, which is really great in case you have any kind of acid or base labile portions in your molecule. And here is the outline of a dipeptide synthesis. So let's say you wanted to make this dipeptide right here, okay? You want to have alanine followed by glycine. So remember, the N-terminus is over here, okay, and the C-terminus is over here. Now I'm going to erase that just so it's not so ugly. But anyhow, so let's say we want to make that. The first thing we have to do is we need to protect the N-terminus of the alanine. And so we're going to treat it with our Bach anhydride or our ditert-butyl dicarbonate. And so we have our Bach protected alanine. Then we want to make a methyl ester. So in this case, he chose a methyl ester. You could have used benzyl as well. So methanol, catalytic amount of acid. And now we have our methyl ester. So now we have our carboxyl group protected on our glycine. So now we have the carboxyl group. And again, I'm scribbling here. The carboxyl of our alanine is exposed. And the amine of our glycine is exposed. And so now when we treat these two molecules, the DCC, we're going to form an amide bond. Now again, I'm going to erase all the scribbling that I put on there, okay? So now we've made our new peptide bond, which is right here between the alanine and the glycine. And so to remove the Bach group, we're going to treat it with TFA. And then to hydrolyze the ester, we're just going to use strong base, just a saponification reaction. Now this method of protecting group, DCC coupling, deprotection is great if you want to make a dipeptide. Sure, you could do that in your fume hood, but if you want to make a bigger peptide, it says here for every amino acid to the peptide 3 reactions and 3 purifications would be necessary. And so Merrifield came up with something that we call the Merrifield synthesis, which is a superior method for reducing the number of synthetic steps greatly. And the way that Merrifield designed it is that the peptide is actually tethered to an insoluble polymer, like a polystyrene type polymer, and we call this solid phase peptide synthesis. So the way this works is that first we start with a protected amino acid and it gets tethered to the beads of this insoluble polymer. And so one such polymer is a polystyrene derivative where we have some CH2Cl groups. So you can see those shown here, right? And these are primary alkyl halides. And so we can do an SN2. So of course you would do, if I can find it here, SN2 like that. So we would tether the NBOC protected amino acid onto the solid phase. So this is a solid here. This is part of a polymer. So now what we can do is we can deprotect, we can remove the Bach groups, and we can do a DCC coupling. And so that's exactly what you see here. First, we do the deprotection with TFA, which isn't shown, okay? Then we couple on this new carboxyl group with DCC, and there you go. We've formed a new amide bond. And so you can just keep going and going and going. And then if you're wondering, well, what do I do once the whole sequence is done? Like once I've made my peptide, how do I remove it from the solid phase support? The way you do that is by treating it with hydrofluoric acid, so HF. In 1969, Merrifield used this technique in the preparation of a protein called ribonuclease, which is comprised of 128 different amino acids. And so the procedure required 369 separate reactions, and he was able to perform them in just 6 weeks. And the overall yield of the entire process, so all of those reactions, all 369 of them, was 17%. Now you might think, well, that's not that great. But remember, you're multiplying all those percent yields together. And so if the overall yield was 17% and we had 369 separate reactions, it implies that each individual step had a yield greater than 99%. And so Merrifield's ingenious method set the stage for an entirely new way of performing chemical reactions. And for his groundbreaking work, he received the 1984 Nobel Prize in Chemistry. Merrifield's solid phase synthesis method has now been completely automated, and we use liquid handlers and robots to do it, and we call those peptide synthesizers. Okay, question 25.37. I'm going to see if I can squeeze all of this onto this one page here, but it says identify all the steps necessary to prepare the following peptide with a Merrifield synthesis. So we have phenylalanine, leucine, valine, phenylalanine again, and remember this is our N-terminus over here. This is our C-terminus here. But remember, the Merrifield starts by using a C-terminus. So we're actually going to start with the phenylalanine first. Then we're going to add the valine, then the leucine. Then we add the second phenylalanine last. So the first step is going to be tethering the phenylalanine onto the polymer. So the way that we represent this is just by drawing the CH2Cl. And then you can write polymer. I like to just put a black dot like that, which represents the polymer. So we're going to take our phenylalanine, our en-Bach protected phenylalanine. So let me just write out the structure of that. And I'm probably providing way too much information, but anyhow. So there's our phenylalanine. Okay, so that's just going to be our SN2 reaction. And then we're going to have our en-Bach protected phenylalanine. So where's my phenyl group? There we go. And now it's going to be tethered to the polymer, just like that. So now we have the first phenylalanine done. So now we're going to tack on the valine. And so remember, we have to remove the Bach group. So for that, we're going to use TFA. So I'll just write TFA. Remember, TFA is the same thing as CF3COOH. You can write it either way, I don't care. So that's going to be the D protection. And then in the second step, we're going to add the valine. So I'm just going to write here Bach valine like this. And then we'll put our DCC reagent. And so now if I can squeeze it in here, we're going to have our Bach group. And then we're going to have our valine. And then we're going to have our phenylalanine. And that's going to be tethered to the polymer, okay? Hopefully you can see what I'm doing here. Maybe you need to zoom in, maybe not. Okay, so let's add the leucine. So to add the leucine, remember we need to remove the Bach first, so that's going to be TFA, trifluoroacetic acid. Then we're going to add the en-Bach protected leucine, so I'll just put here Bach leucine like this. And we need our DCC, of course. And so now we're going to have our Bach group, and it's going to be attached to our leucine, which is attached to our valine, which is attached to our phenylalanine, and of course that's tethered to the polymer. So now we have just to add that one last phenylalanine, and so for that, hopefully I'm not running out of space here. Anyhow, number one, we're going to treat it with TFA, and number two, we're going to treat it with our Bach protected phenylalanine and DCC to do our coupling. And so now we're going to have our Bach group, and it's going to be attached to our first phenylalanine, or maybe our second phenylalanine, I guess. So phenylalanine, then we have our leucine, then we have our valine. It's not time consuming or anything, right? Then we have our polymer. Okay, and so to remove the Bach group, we're going to use TFA. And then to rip the whole thing off of the polymer, we're going to use HF. And so that it's going to give us our tetrapeptide. I'm going to try to be as neat as I can here for the final answer. And so we're going to have our phenylalanine, our leucine, our valine, and our phenylalanine. So that's just kind of an intro to Merrifield. And again, you won a Nobel Prize for this, the Merrifield synthesis. And so now chemists have all kinds of cool peptide synthesizers out there that can make these compounds really quickly and at very high yield, so very effectively. Very cool chemistry.